Hello. This little mini lecture is going to be on energy and work. um, it's a little different from what we've done so far with kinematics in that energy is a scalar. So in general, people find this topic to be easier than what we've done so far in mechanics. Okay, so our basic energy model is that we are going to define a system and it can be whatever you just decide that to be. So a system's going to have some boundaries that conceptually we would think about it being isolated from the outside environment. And within that system, then energy can transform between different types. So we'll talk about three different types of energy: kinetic energy, potential energy, and thermal energy. Energy can go back and forth between kinetic and potential. Once it goes to thermal, that's a one-way street. It can't come back out into kinetic or potential. And then, so that's our system. And then we can actually add energy into that system or take energy out, and that's what we call work. Okay, so let's look at the forms of energy in a little more detail. So kinetic energy you may have seen before. It's the energy associated with motion, depends on mass and speed, and this is the equation for it right here. So kinetic energy is 1/2 the mass times velocity squared. Potential energy has different forms, but basically we want to think about any of those as energy that's stored. So it's energy that could be available to be converted into motion. It depends on the object's position, and the examples that we will use are gravitational potential energy and elastic energy, sort of the energy that's stored in spring. And then in the next chapter, in 10, we'll talk more about thermal energy, but this is energy that's kind of dissipated, maybe through friction. It goes into heating up objects or maybe motion at the atomic scale. And like I said, once energy transforms into thermal, we don't get it back into kinetic or potential. Energy has its own unit called joules, and it is a product of the Newton times meter. Okay, so 1 joule is 1 Newton meter. And I'm just going to quickly mention power. We're not going to do a lot with it in this lecture. Power, just to as a definition, is energy per time. We could kind of rewrite that as force times velocity as well. Power is measured in its units of watts, and 1 watt is 1 joule per second. Okay. All right, so we're going to focus on work now. Work is the concept of work, at least the way that we're going to talk about it in this class and in our textbook. So we mentioned that we have a system that's isolated where kinetic and potential can go back and forth into different forms. Thermal energy is a one-way street. We can actually add energy into our system then, and that's what we define as work. So work is energy added or removed from a system. So it can be positive, where we would actually increase the energy of the system by adding energy in, and work can be negative as well, where we would decrease the energy of the system. So if we add all this together now, we get an expression for conservation of energy. So it says the change in energy of our system would be any change in kinetic energy or change in potential energy, change in thermal energy. And if the energy of the system changes, that means work must be done on the system, right? Or the system does work on the environment. So this could be plus or minus. Okay, so let's look at work in a little more detail. So its official definition is that work is the dot product of force and displacement. And a dot product we're going to look at down below, but the symbol for it is this little dot here. It's the one way of multiplying vectors. Okay, so we're actually multiplying the force vector with the displacement vector. And it's a special multiplication process. So when force is constant, which again will be the case for everything except springs, we can rewrite the equation for work as this. And this is kind of how we're defining what the dot product is for you. So we take our vectors here, right, force and displacement, and we write them out in their 3 components, right? Just for completeness here, we're doing X, Y, and Z, although this semester we don't do a lot of 3-dimensional stuff. We keep our dot product symbol, and then we have delta X, delta Y, and delta Z, right? That's our displacement. We could say delta R. In the book it says delta S. Those are equivalent. It just means displacement. Okay, so what the dot product does then is just takes this top row, multiplies them together, right? So fx times delta x, and then it adds it to the product of the middle row, so fy delta y, and then we add that to the product of the bottom row, fz delta z. So once you get the vectors in their component form, the dot product is actually really easy to compute, right? It's just the x components, the product of the x components, plus the product of the y components, plus the product of the z components. And that could be for any vector, right? Any random vectors, that's how you would compute the dot product. Okay, so let's do an example here. So we have a 20 Newton tension force applied to a suitcase as shown below. Calculate the work done by the tension force as the suitcase is displaced 100 meters. Okay, so let's try and plug this in and it will give us an example of how we actually use the dot product as well. So I'm going to write my information down so we know that the tension, if we write down what we're given, we have tension is 20 newtons. We have the displacement, delta x, is 100 newtons. We have the angle, theta, between tension and the x-axis is 45 degrees. And I think that's everything we know. Okay, so let's switch to the camera and we'll calculate this out. Okay, so that is what we're given. And again, we'll just draw our suitcase here, right? It's on the ground. And it's being pulled by tension at a 45-degree angle. And then the question is, if we drag that along for 100 meters, what is the work done? Okay, so work is, and this is a constant force, right? It's not varying as we change the position at all. Okay, we're saying that this is our x direction and that's our y direction. Okay, so work is a scalar, right? So this is not a vector, but it is the product of force, which is a vector, and displacement, which we could say delta r, delta s, whatever makes you happy. Okay, so let's write out our vectors here. So this is just 2D. I'm not going to put the third dimension in. My x component of tension is going to be t times cos 45 degrees, and then t times sine 45 degrees for the y component. And then I'm going to dot that into my displacement, which would be delta x and delta y. Okay. There is no displacement in the y direction, it's just delta x. So now when I take my dot product, right, I'm going to multiply these together. So it equals t cos, let me just put it as theta right now, times delta x, plus, and I'll just write it out as well, just for completeness. So t sine theta, delta y, right? And we said that's 0, so that term goes away. So we get t cos theta delta x, and now we can plug in. We have 20 newtons. We have cosine of 45 degrees, and we have a displacement of, oh, that should be meters, not newtons. 100 meters. Okay. And then let's calculate it. I'll pull up our Python window. So we have, I'm just going to define my theta here because Python likes units in radians. Theta is radians of 45 degrees. And then we'll say our work, right, is 20 newtons times cosine of theta times 100 meters. Okay, so I get, we'll just keep 3 significant figures, 1410. And my units now are Newton times a meter. That's a joule. Okay, so that's an example of calculating work and how you use the dot product. let me actually just go back here and say another definition of work, right, which we can see that we've done here, actually, is that sometimes you'll see work defined as the force times your displacement. So we'll say delta x, and this is just a regular times now, not a dot product, times the cosine of the angle between them. So between the vectors of force and displacement. Okay, when we do the dot product out like this, that happens automatically. You might also see it as that work is the force parallel to displacement times displacement. Right. So really, what we're doing with tension, what these are saying is that you're going to take this component. If my displacement is in this direction, because I just had a delta x, my component of the force that's doing work and actually moving the object along is only this part. Okay, so sometimes that's written as the force component of the force parallel to displacement. Again, with theta here, it's also the force times cos theta. Okay, so those are different ways to think about work. So depending on the problem, you might want to use some of these other definitions as well. Okay, so it's good to keep in mind that work can be negative if either the force or displacement are in different directions. So here's a case that you're looking at an object, a point particle, in two different positions. So here's one and here's the other. So the blue is showing us the displacement between the two positions. And this is showing us velocity initial and velocity final. So you can see that the velocity has decreased. And if we look at the force in this case, right, displacement is to the right, force is up at some angle theta, but its x component is negative. So if we look at our work equation, right, we have the dot product of force times displacement, which is our components, x, y, and z, with our displacement, delta x, delta y, delta z, and then we just multiply all the corresponding pairs, right, and add them together. When we put in the x component of force, right, it's going to be negative because it's going, again, with the convention that x is positive to the right. So in this case, right, when we multiply that out, so delta x would be positive, the force would be negative, so we'd get a negative work. And we see that in that if the system is our particle and it had kinetic energy, that kinetic energy went down. Okay, so the energy of the system went down because work was negative. So just to review here, the x component of the force is negative, the x displacement is positive. So when these are in different directions, the work ends up being negative and the object will be slowing down, where the system loses energy. Okay, so everything we've done so far was for a constant force, but we do have one example that we'll work with a variable force, and that is for springs. And so the true definition of work is actually it's the integral of F dotted with the displacement vector. Okay, so I know some of you are just in the first semester of calculus or in pre-calc, so don't panic when you see the integration here. What we'll do in practice is use a geometric interpretation of integration, which is just to calculate the area under the curve. Okay, so when we have a variable force, like is shown here, the force is decreasing with position, right? So it's not just a constant value. The value of the force depends on position. So we'd have to think about the fact that it is not just, you can't just do F dot delta X, right? So it's actually a variable. So what we would do here is just to integrate this area under the curve. And to do that, we'd say, well, this looks like a triangle. So the area under the curve is what an integral is. And so it's just 1/2 the base times the height, right? So we have 1/2. The height is 5,000 newtons and the base is 200 meters. Okay, so that's what the work will be in this example. Just as a comparison, right, if we had a constant force where it's not dependent on position at all, we can still think of it as that work is the area under this curve. It's just that it's a really simple area, right? It's just a rectangle. So it's the force, which is constant, times the displacement. So that's what we've been working with before. So they're really equivalent. It's just we've been using a simplified version for when the force is constant. Okay, so we said springs are one example where the force varies with position. And so here's a little cartoon drawing of someone pulling down on a spring to stretch it. And you can see as the spring stretches, the force that you need to stretch it even more will keep increasing. And so we can just plot that up as a curve or a relationship between how much we're stretching it, which would be shown on the x-axis here, and the force required to stretch it. So as we stretch it more and more, the force required keeps increasing. And this is known as Hooke's law. Okay, so officially Hooke's law says this is the force exerted by the spring, right? So this plot here is the force that you would exert to stretch the spring a certain distance. As you're stretching the spring is pulling back on you, right? So it doesn't want to get stretched. It wants to go back to its natural length. And that's what's expressed here in this equation. So the force exerted by the spring has a negative sign. Okay, so it will, because if you stretch it to the right, it's pulling back to the left. That's the sense of the negative sign. So it's just equal to some constant that is a property of the spring and how tightly it's wound and the material it's made out of, times the displacement. Okay, and that negative sign, like I said, indicates it's the restoring force. So if you stretch it to the right, it wants to pull back to the left till its original length. Okay, so it's just good to keep in mind when if you're thinking about the force you exert on it, there wouldn't be a negative sign. But if you're thinking the force that the spring exerts back on you as you're pulling it, there is the negative sign. Okay, so we can use our understanding of work and our conservation of energy equation to derive the energy stored in the spring. And just to give you a sneak peek, it's just 1/2 the spring constant K delta x squared, which is how much you're stretching it. Okay, so let's do our graphical analysis first, right? So we had a couple of slides ago, we had a conservation of energy saying that if our system changed, and our system is just going to be the spring, it means that we've done some work on it. Okay, and we can then use our concept of work as the area under the force versus displacement curve, right? So this is a little overkill for this example, but let's say we wanted to calculate the work between 3 and 1, right? How much work, or what was the change in spring's energy between position 3 and position 1? So we would do the big triangle, right? It would be the area marked by the point 3. So our force would be spring constant times our displacement, and then so that's the y-axis, and our displacement would just be x. And so again, it's the area of a triangle, 1/2 base times height. And then if we just wanted the difference between these 2 points, we'd have to subtract out the energy already stored in the spring when it was stretched to 1. So again, we just have another triangle, 1/2 base times height. Our base is the x value there. Our height is the force at that value, which is kx, and we have a 1/2. And then if we complete our algebra, we get 1/2 k x final squared minus x initial squared. Okay, so we can also do this with calculus if we plug in here. So it is, and this is all one dimension, so the dot product just becomes the force in the x, let's say in the x direction, kx times the displacement delta x. So for those of you who have done integration before, it's just x to the n. The integral of x to the n is x to the n plus 1 divided by n plus 1. So we get 1/2. The k is a constant that just comes out, and we get x final squared when we evaluate it between these two, x final and x initial, right? So x final squared minus x initial squared. Okay. So work-kinetic energy theorem says that the net work done on a particle causes a change in its kinetic energy. So that's expressed right here, right? So change in kinetic energy is the net work. And we would do this actually for every force that's acting on a particular object. And again, just repeating here the definition, right, of the dot product. So we keep that in mind. And then just to explicitly write that out, our change in kinetic energy, right? Kinetic energy is 1/2 mv squared. So our delta is always going to be final minus initial. So 1/2 mv final squared minus 1/2 mv initial squared. And if we just look at that in a little more detail, right, and expand that out a little bit, And again, just thinking about this in one dimension, just to simplify things. So this is what we said, our change in kinetic energy is the work done. We already put that down here. So 1/2 mv squared minus 1/2 m v initial squared. So v final squared minus v initial squared. And the work just in the x direction will be the x component of the force, delta x. Okay, force is mass times acceleration, right? Delta x just comes down, everything else just comes down here. And then we're going to just multiply through by 2. So we get mv final squared is mv initial squared 2 ma, right? That came from our force times delta x. And then we can divide through by mass. Everything has a mass, right? So we can divide the left side and the right side by mass, and we get this, v final squared minus v initial squared is 2a delta x, which is pretty cool. That's the kinematic equation we've been using for quite some time, and now we can see that it actually comes from energy. Okay, example 2, let's do this one. So we're gonna just practice here. This will be the end of the video. We're gonna just practice calculating the change in kinetic energy from work using the work-kinetic energy theorem. So we have a skier, okay, with mass of 70 kilograms, is gliding at 2 meters per second. So the initial is 2 meters per second. When he starts down a very slippery slope, I'm going to call that delta x because it's in our x direction, is 50 meters. And the incline is 10 degrees. Okay, and then calculate the speed at the bottom. Okay, so let's switch to our camera. Okay, so that's our givens, and we want to find the final, which is in the x direction. Okay, so that's our theta. We have our skier here. Okay, we sum the initial. And we want to know down at the bottom what's the final. Okay, so we're going to do that, use our work-kinetic energy theorem. So the net work is change in kinetic energy. So to get the net work, we want to do our free body diagram. So we have force of gravity going down, we have the normal going up, and then I kind of drew this be a lot steeper than it is, and that's theta. Okay, and this is our x direction, and that's our y direction. Okay, so let's just quick break our gravity into components. So just do that a little bit below, right? So if that's my FG, and so that's my part down the incline, that's my part. Just continue it out. That's theta there. This is 90 minus theta. This is 90. Here's theta inside here, because this is also 90 degrees. Okay, this is the force of gravity. This is my x component. This is my y component. And we have FGX is FG sine theta, FG y equals FG cos theta. Okay, so then our net work is going to be the normal dotted with our displacement plus force of gravity dotted with our displacement. Okay, so let's write those out in component form. So my normal is in the y direction, doesn't have anything in x, so 0x, positive n in the y. And my displacement is just a delta x, right? Delta x and delta y is 0. Okay, and then my force of gravity, I have my x component, fg sine theta, fg cos theta, And my displacement is delta x, again, and delta y, same thing. Again, that's 0. Okay, so when I calculate my dot product, this is 0, right? So I get, just to write it out for completeness, 0 times delta x plus the normal times 0 for delta y, plus fg sine theta delta x plus fg, see if I can fit it in here, cos theta delta y, which is 0. So 0, 0, 0. And we can think about that physically, right? So the only force or component of the force that's speeding up the object, right, and adding energy to the system is this component of gravity going down the incline. So my net work then is Fg sine theta delta x. Okay, and we're going to use our work-kinetic energy theorem. So the net work equals change in kinetic energy. This is 1/2 m v final squared minus 1/2 m v initial squared is our net work, which we said is Fg sine theta delta x. So we could calculate that right here if we want, or we could just do all of the algebra. So f of g, right, is mg sine theta delta x plus 1/2 m v initial squared equals 1/2 m v final squared. This is what we're trying to solve for. Okay, every term has a mass in it, so we can divide through by mass. Okay, and we get, and we can also multiply through by 2. So we get 2g sine theta delta x plus v initial squared equals v final squared. And then we would take the square root of both sides. V final is the square root 2g sine theta delta x plus v initial squared. Okay, so let's calculate that out. So we'll just set g equals to 9.8. The initial equals 2. Delta x is 50. Theta is 10 here. Okay, so then we want to do square root. These are all NumPy functions, by the way. So 2 times g times np bet sine of theta times delta x plus v initial squared. That will give us the end velocity. So we get v final 13 point, if we just keep 3 significant figures, we say 13.2 meters per second. Okay, and if you did want to calculate the work done as an in-between step, right, that would be, our mass is 70, so it would be m times g times sine of theta times delta x. And it would be a Newton times a meter, which is a joule. Okay, so if you want to calculate that as a in-between step. Okay, that is the end of the lecture. Let me just show you, yeah, we'll stop there. One other way to do that is to do, you could try it on your own using the work is force times displacement times the cosine of the angle between them. You'll get the same result. Okay, thanks for checking in.